Welcome to G Fun Facts Online. Today we are looking at the future of interplanetary energy. The history of human exploration is, at its core, a history of logistics. If you look back at the Polynesian voyagers navigating the vast Pacific, their success depended on carrying coconuts and taro, plants that could sustain them and grow in new lands. If you look at Roald Amundsen's expedition to the South Pole, his survival relied on the carefully calculated caloric math of sled dogs. The rule has always been simple. The success of an expedition hinges on the ratio of what you bring versus what you can find when you get there. But as humanity stands on the precipice of becoming an interplanetary species, the old rules of logistics are breaking down. We are facing the tyranny of the rocket equation. This physical law dictates that for every single kilogram of payload we want to send to Mars, we need huge amounts of fuel just to lift it off Earth. This creates a vicious cycle where fuel adds weight, requiring more fuel, adding more weight. This makes the prospect of hauling heavy, dangerous infrastructure across 140 million miles of vacuum not just expensive, but potentially prohibitive. And the heaviest, most problematic item on the packing list? Batteries. If we are to settle the red planet, we cannot simply bring our power grid with us. We have to build it there, from the dust beneath our boots. Enter a breakthrough that sounds less like high-tech aerospace engineering and more like ancient pottery. A battery made of water, clay, and graphene. This is the story of the Blue Battery, a development recently published by researchers at the Swiss Federal Institute of Technology, or EPFL, and the University of Manchester. It promises to upend our understanding of energy storage. It does not rely on rare earth metals, toxic lithium, or complex chemical supply chains. Instead, it wakes up the dormant electrical potential hidden in the most mundane materials in the universe. To understand why a clay battery is revolutionary, we must first look at the fragility of our current champion, the lithium-ion battery. Lithium-ion batteries are miracles of modern engineering. They power our electric vehicles and our smartphones efficiently on Earth. But in space, they are absolute divas. They are prone to thermal runaway, which is a polite scientific way of saying they catch fire if punctured or overheated. In a pressurized habitat on Mars, a fire is a death sentence. Furthermore, they degrade. Every time you charge your phone, the battery dies a little bit. Over 10 years, a lithium-ion grid would lose significant capacity. And critically, they require lithium, cobalt, and nickel, materials that you either have to mine with heavy industrial equipment that you don't have on Mars, or ship from Earth at astronomical cost. Elon Musk's Starship might lower launch costs, but it cannot change chemistry. If a Mars colony's battery array dies after 10 years, and the replacement shipment is 6 months away, the colony dies. We need energy storage that is ubiquitous, chemically stable, and effectively immortal. The solution, surprisingly, comes from a convergence of nanofluidics and geology. Researchers led by Vasily Artemov have detailed a device that uses ultra-confined water as its electrolyte. The science behind this is as bizarre as it is beautiful. It relies on the strange behavior of fluids at the nanoscale. On a human scale, water is simple. It flows, it makes things wet, it freezes at 0 degrees Celsius. But the physics changes when you squeeze water into a channel that is only 1 nanometer wide. For context, that is a space barely large enough for a few molecules to squeeze through single file. At the University of Manchester, which is famous as the home of graphene, researchers discovered that water in these tiny spaces stops behaving like water. It develops a split personality. Perpendicular to the surface, it becomes electrically dead, acting as an insulator. But parallel to the surface, its conductivity skyrockets. The water molecules align in such a way that they facilitate what is called proton superconductivity. This means protons, or positive charges, can zip through the water chains with almost zero resistance. The Blue Battery capitalizes on this quantum mechanical quirk. It is composed of three main parts. First, the electrodes are made of graphene, the Nobel Prize-winning supermaterial made of a single layer of carbon atoms. Second, the separator is a nanostructured layer of clay. And third, the electrolyte is simply pure water, trapped within the microscopic layers of that clay. When voltage is applied, protons and hydroxide ions separate and accumulate at the graphene electrodes, storing energy. But here is the key difference. Unlike a chemical battery that degrades the electrode material, like lead acid or lithium-ion batteries do, this mechanism is purely physical. The ions move, but the structure doesn't break down chemically. This suggests a battery that could theoretically run for a very, very long time. Now, let's look at the ingredients through the lens of a Martian settler. Why is this specific chemistry the holy grail for Mars? Because the recipe is practically written into the Martian landscape. Let's break down the three components: the clay, the water, and the graphene. First, the clay. Mars is often called a rusty world, but its geology is rich in phyllosilicates. These are clays formed by the interaction of volcanic rock and ancient water. The blue battery relies on van der Waals clay nanostructures. Specific clays used in Earth trials, like sepiolite and montmorillonite, have geological analogs right there on Mars. A rover wouldn't need to prospect for rare veins of ore or dig deep mines. It could simply scoop up regolith, the Martian soil, process it to isolate the clay minerals, and sinter them into the necessary nanostructures. Second, the water. We know Mars has water. It is locked in the massive polar ice caps and buried in subsurface glaciers. While water is precious on Mars for life support, using it for batteries is highly efficient because this technology doesn't require the water to be chemically refined into a complex acid or gel. For the blue battery, the water just needs to be purified and injected into the clay matrix. Third, the graphene. This sounds like the hard part, as graphene is a high-tech material. But remember, graphene is just carbon. Mars has an atmosphere that is 95% carbon dioxide. Several technologies already exist to strip carbon from CO2. The Sabatier reaction is already used for fuel production plants. Furthermore, researchers at TU Delft are exploring bacterial processing, using microbes like Shionella to reduce graphite oxide into graphene. We could literally grow our battery components in vats or pull them out of the thin air. However, we must be realistic about performance. In the world of batteries, there is always a trade-off. The current iteration of the Water-Clay-Graphene battery has an energy density of around 10 watt-hours per kilogram. To put that in perspective, a Tesla Model 3 battery has an energy density of roughly 250 watt-hours per kilogram. If you tried to power a Mars rover with clay batteries, the battery would be so heavy the rover wouldn't be able to move. For high-energy mobile applications, the clay battery loses. This is where the concept of the Mars-breathing battery comes into play. A competing innovation from the University of Science and Technology of China recently developed a lithium CO2 battery that literally breathes the Martian atmosphere to generate power. It achieves a staggering 373.9 watt-hours per kilogram. That is vastly superior to the clay battery. So why bother with the low-energy clay battery? The answer is longevity. The high-energy lithium CO2 battery has a lifespan of about 1,375 hours. That is less than 2 Martian months. It burns bright and dies young. The Water-Clay-Graphene battery, however, has demonstrated 60,000 charge-discharge cycles with nearly 100% efficiency. If you charged and discharged it once a day, every single day, it would last for over 150 years. This creates a perfect symbiosis for a colony. You have the hare and the tortoise. You use the high-density breathing batteries for rovers, drones, and spacesuits that need bursts of power and can be replaced. But for the baseload, the life support, the heating, the lights, you use the tortoise. You use massive, heavy, stationary banks of clay batteries buried underground. They never need replacing. They don't catch fire. They just work for generations. The most exciting implication of the water-clay battery, however, is that it blurs the line between energy storage and building material. On Earth, a battery is a box you hide in the basement. On Mars, space is tight. Because the blue battery is made of clay and carbon, it is mechanically robust. We are approaching the concept of structural batteries. Imagine 3D printing the walls of a Martian habitat, not just with inert concrete, but with energized clay. The walls themselves could store the energy harvested by solar arrays during the day to keep the astronauts warm at night. The physical shelter becomes the power bank. This concept, often called starcrete or functionalized regolith, turns the problem of battery weight into a solution. The mass is useful because it provides radiation shielding and electricity simultaneously. While the red planet provides the perfect use case, the implications for Earth are equally profound. We are currently rushing to electrify our grid, but we simply do not have enough lithium to build grid-scale batteries for every city on Earth without causing massive environmental damage. The blue battery offers a green alternative. It is non-toxic, recyclable, and made of mud and water. For stationary grid storage, where weight doesn't matter, but cost and longevity do, this could be the technology that finally makes wind and solar viable 24/7. The colonization of space will not be powered by the exotic technologies of science fiction. There are no antimatter drives or zero-point energy generators here. It will be powered by the mastery of the fundamental blocks of matter. It comes from the realization that water, when squeezed tight enough, becomes a superconductor of protons. It comes from the realization that the dust of a dead world can be baked into a vessel for life. The water-clay-graphene battery represents a shift from importing survival to manufacturing survival. It is a humble technology, literally made of earth and water, but it holds the key to a civilization that can endure, not just visit, the stars.